Welcome to solving trigonometric equations. We're going to be using some of the formulas here, and let's go and take a look at the first equation. We basically are going to solve these just using normal geometric equations, normal algebraic techniques, such as subtracting on both sides, or what we call the property of equality. So the sine of x, and x is used to mean an angle, or we can use theta or alpha. So there are other things that are common. I don't mean for those to go. Welcome to solving trig equations. This formula list, there's many things on here we'll use in doing some of these solving equations. But let's go to a basic one that emphasizes how we will simply be doing normal algebraic techniques to do it, such as subtracting 2, so that the sine of an angle is equal to 1. By the way, x can be used for an angle. We're used to theta also, even alpha or anything else. Alpha, beta, there's a number of things that can be used. Here it's just normal x. In this case, it's what we're trying to find. So we need to find the places where x is equal to 1, and we have a restricted domain using interval notation, including 0 around the unit circle and not including the end. But since they happen to be the same place, it really won't matter here. So when you think about looking at it, or if you apply sine minus 1 of 1, that means we end up with 90 degrees or pi over 2. But in this case, because the restricted domain is showing us that we're using degrees, that means the answer should also be in degrees. Now, let's take a look at something that's a little bit more complicated. Oh, wait a minute. Actually, let's talk about it with all solutions. Because in this case, we were only going around the unit circle once. But we could have come to 90 degrees and come around again, and come around again, and again, and again, or gone backwards numerous times. So we have to show that. What we have to show is that the answer would be 90 degrees plus 360. That would give us 450, plus 360 again, plus 360 again. So if you think about it, this is one turn around, this is two turns around, three turns around. So it's like however many turns you want. Even 90 degrees is plus 360 times 0 turns around, because you're not adding 360 at all. So the way we would say it is 90 degrees plus 360 times n, and n is the number of times that we rotate around the unit circle. So it was sine of x is equal to, or x is equal to, the angle is equal to 90 degrees plus 360n. And that's the way that you show an infinite number of solutions, actually, because you could also go backwards. If n is going backwards minus 1 time, we'd be doing -1. So subtracting 360 would give us a -270, which is also the same place where 90 degrees is. So we'll be using this a good deal. And on each of the problems here, we're going to be doing a restricted domain and a find all solutions. You always look at for a test question, you would look for what's being asked in order to answer it, and not do both, only do what you're told to do. Solve for an angle. So sine of theta times cosine of theta minus 1/2 cosine theta. Oh, and then I think something's off. I think that's supposed to be an equal. Take a look. Oh, I forgot to put down that that's supposed to be equal to 0. So let's add that. This is equal to 0 here, right? So that part's not added. Please add that yourself there. So when I look at this now, I can see that I have sine of theta, and then I have a cosine theta minus 1/2 a cosine theta. So I actually have something in both of these. That's sort of like x times y minus 1/2 y. I can take y out of both of those like this. And that's what I'm going to do with the cosine. So I'm going to take cosine of theta out of that and have the sine of theta minus 1/2, and we're equal to 0, which I didn't add, but now you see it's there. And now what we can do is Multiplying it, this is where we have that a times b is equal to 0. If that's true, then one of them has to be equal to 0, or both of them. So we separate them, give them each zeros, and solve them. So we're going to do just that. Cosine of theta is equal to 0, or the sine minus 1/2, sine of theta minus 1/2 is equal to 0. So let's solve for that. Cosine minus 1, 0. What are the places where that's true? Oh, and we're dealing with radians here. So we can do angles and then replace it or not. So for 0, the cosine is 0 at 90 degrees and at 270 degrees, which is pi over 2, and 3 pi over 2. For this one, we'll add 1/2 to both sides. And then say sine minus 1 of 1/2 is what places. So when we think of the unit circle, the sine is 1/2 at 30 degrees. 1/2 at 30, pi over 3. So I'll say 30 degrees, and I'll say pi over 3 underneath it here. Yeah. And then it's 1/2 at all the other places. Let's say it's 1/2 at that. It's also 1/2 at 150, which is 5 pi over 6. And then, let's see, and that's the only places where it's positive 1/2. It would be negative 1/2 in other spots. Now we have 4 answers here. Let's look at the restricted domain. For the restricted domain, we're looking at pi over 2 from here, going around to 3 pi over 2. So we're looking only here. If we're looking at only here and it is equal to, so since it's equal to, then the pi over 2 here will work. And since it's equal to, the 3 pi over 2 will work. But pi over 3 isn't, because pi over 3 is over here. And 5 pi is over 6 is over here. So that's okay, because that's inside the correct, what we want, the correct quadrants that we want, the restricted domain. So we have 3 answers. Theta is equal to, and let's start with the smallest one, pi over 2. And then the next largest, 5 pi over 6, and then 3 pi over 2. Now let's do the find all solutions. Okay? And it's going to be an interesting thing to deal with, because let's take the first one, pi over 2. All we have to do is add 2 pi to it and 2 pi n. And that's going to give us all the possible solutions going around and around and around. And then we'll do it with 5 pi over 6 plus 2 pi n. And then 3 pi over 2 plus 2 pi n. Now, something about pi over 2 and 3 pi over 2 is that here I can go around one time with 2 pi. But if I'm at pi over 2, I can simply go around by pi and get to 3 pi over 2, and then pi again, and then pi again, and then pi again. So these two could be combined by doing pi over 2 plus pi n, because that's going to include every place where it's 90 degrees, and because it goes only halfway each time, it's going to include every place that has 270 degrees, or 3 pi over 2. So the best, so this, and this would still be correct, but it would be a better answer to say pi over 2 plus pi n and 5 pi over 6 plus 2 pi n. See, we can't do it with 5 pi over 6 because there's nothing over here that matches it there. It's just that one place here. That way. It's just that one spot there. So that would be the best of the answers, to say pi over 2 plus pi n. When you recognize it, it's really cool to be able to write that to combine 2 of these. But doing all 3 separately is also acceptable. It's just not quite as cool. Okay, let's take a look now at page 4. So now we're going to solve, and this is a different one. In fact, let's go back here. Notice the technique for solving this was to take out a common factor and then to use what we call the zero product property. So those 2 things, that was the key. Those were the 2 key things to solve this one. The one before it the key thing was subtracting on both sides or using what's called the property of equality. Okay, so we have different techniques we've used so far. Now look at this one. This one looks suspiciously quadratic. In fact, if I did something different instead of cosine, let's say I did x squared plus 2x plus 1 is equal to 0. Oh, we could just factor that. That's just a factorable thing. X squared plus 2x plus 1 happens to be x plus 1 squared, actually, x plus 1 and x plus 1 again. So it's like the same thing. Well, that means that this can become cosine of theta plus 1 times cosine of theta plus 1 is equal to 0. And actually, because it's squared, we don't really have to do both of them. We'll just do one of them. Cosine of theta plus 1 is equal to 0. Now we'll subtract 1. Subtract 1. And look and see where is the cosine of an angle -1. There's only one place where it is, and that's at pi. So on the unit circle, you see at this place here, it's -1 and 0. And that's the only place where cosine is -1. So that means that the angle is pi or 180 degrees, but since the restricted domain is in radians, we will use the radians answer. Now, when we do the all solutions, then we'll say that the angle is pi plus 2 pi n. And that's the one we use for the radians because 2 pi gets you around one time, and n, the number of times that you want to go, would be that. Let's fill that one in. Let's go to page 5. Yeah. So here's another different one. Now we have coefficient, we have a square, we equals the 1/2. First thing we can do, I can see we have that 2. Let's divide both sides by 2. Okay, or multiply by the reciprocal of it. So what I'm going to do here is I'm going to multiply by the reciprocal. I'll multiply by the reciprocal. There's other ways I could look at thinking of this, but I want to get the cosine squared x by itself. Okay. Now, since that's actually just a square, in reality, we have cosine x squared equals 1/4. So what we can do now is to take the square root of both of them. So the square root of both of these, in fact, I want to do these, show them as separate equations. And it has to be plus or minus. That gives us cosine x, because that square and square root cancel out, is equal to plus and minus. The square root of 1 is 1, and the square root of 4 is 2. So where is, and actually now, the cosine is positive 1/2 or negative 1/2. Well, what we want to figure out here, we're between 0 and 2 pi. We're using the whole unit circle. So it could be positive or it could be negative. So what we need to do is do two separate problems. Cosine of x equals 1/2 and cosine of x equals negative 1/2. So cosine minus 1 of 1/2. Those angles where that's true is pi over 3 and 5 pi over 3 on the unit circle. Cosine minus 1 of negative 1/2. On the unit circle, you see that at 2 pi over 3 and at 4 pi over 3. So we have 4 answers, all of which are good acceptable answers. Okay, now let's think about where they are. So actually, first, here's our solution. I'll do them as a solution set. Let's see, pi over 3 is the smallest of these. And then these are all the 60-degree various angles. So 2 pi over 3, 4 pi over 3, and 5 pi over 3. Now what that means, that's a 60-degree and a 120, and then the 240, which is down here, and the 300, which is over here. 40, 60, yep, 300. So those places, that means these are here. This one's pi over 3. All I have to do is add pi to that to get around to this one. So instead of doing 2 pi, I would do pi over 3 plus pi n. And this one is 2 pi over 3. So again, that one I would only add pi to get over here to 5. Let's see, this is 5 pi over 3. And this one was 4 pi over 3, just to be, we'll put them in there. So I'd be adding pi to it. So I would have 2 pi over 3 plus pi n. And that would actually be, those would actually be the solutions for all possible answers. Okay, all possible solutions. I could do them separately, but that feels like a waste when I can put them all together like one like this. Okay, now let's take a look at page 6. I forgot to put the theta in here, so please put that in as you're watching and doing these. So now when I look at this, well, let's see, that looks like maybe it could be, oh, I have -1. What am I going to do with this one here? Okay, this is cosine and this is sine, so it's not like the problem was above where I factored it. Like when I factored this one, I could do it because it was the same thing. It was cosine and cosine because it has to be like x and x here. You can't have different variables. There. Let's come back down here. I now have a problem because I have sine here and I have cosine here. So what I could instead think about is using something of the various formulas. So let's take a look at the Pythagorean identity. Sine squared plus cosine squared equals 1. Well, here I have a cosine squared. So why don't I, of course, this is theta. I keep forgetting to write that now, but anyway. Let's subtract the sine. Cosine squared theta is 1, and subtract that from both sides. 1 minus sine squared theta. Well, I get to put that over here. Instead of cosine squared theta, let's put 1 minus sine squared theta plus sine theta minus 1 is equal to 0. So I just replaced cosine squared theta with that. That looks pretty good. I've got something that got them the same thing, which I want to do. Let's multiply the 2 in here. So I get 2 minus 2 sine squared theta plus sine theta minus 1. So 2 take away 1. Let's do these things. So now I'm at -2 sine squared theta plus sine theta plus 1 is equal to 0. Because I get 2 take away 1 for that. That pesky negative, I don't like how using, and we're not supposed to actually use a negative. So for the first one, so let's multiply both sides by -1. There's nothing wrong with doing that at all. In fact, what it does for us now is it gets rid of the negative that's here and gives us a positive to lead this thing off, which you always want. It does change the signs of the other ones, but you can't help that for nothing, but it's perfectly okay. But now we have a quadratic and we want to see, can we factor it? If we think a sine is x, this is like 2x squared minus sine, just 1 sine theta, so it's minus x minus 1. So it's like that one. So I have to think, how would I factor that? I would have a 2x and an x to multiply to make 2x squared. And I need a +1 and a -1. So a -1 here and a +1 here would give me a minus x. So it looks like I factored it, 2x plus 1 and x minus 1. All I need to do is, instead of x, I put sine. So I come back to here, and what I have is 2 sine plus 1. Oh, let's do it with theta. Let's do that a lot neater, in fact. Okay. 2 sine theta plus 1 and sine theta minus 1 is equal to 0. So here is sort of the key step. I got down to this point, so look at what I had to do. I had to replace that, or put that in place of the cosine squared. And then I had to combine a couple of numbers, and then I had to use the -1 on both sides to get rid of the negative there, because then I got into a place where this was factorable. And now that I have it factored, now I can do the two separate things equal to 0. 2 sine theta plus 1 is equal to 0. sine of theta minus 1 is equal to 0. So if I subtract 1 from both sides, 2 sine theta equals negative 1. Let's divide by 2. Sine of theta equals negative 1/2. Over here, I add 1 to both sides. Sine of theta is equal to 1. So let's find where those things are true. And this one, I'm going to go over and give some space there, take some space there so I can leave this one. For this one here, the sine of theta is negative 1/2 at 2 places, 7 pi over 6 and 11 pi over 6. Okay. The other one, sine of theta equals 1, it's only 1 at one place, and that's at 90 degrees or pi over 2. So we have 3 answers. And in fact, it's best probably if I put them in this order like this here. So it's pi over 2, 7 pi over 6, and 11 pi over 6. And now for these, let's think about where they are on a unit circle. One of them is up here, that's pi over 2. Okay. And let's do this. This one's down here. Okay, that's 7 pi over 6. So it's like 90 degrees. Okay. And over here, that's 210 degrees. And then over here, that's 330 degrees. So I noticed something that this is a 120 difference, 120 degrees difference. And this one's a 120 degrees difference. And this is a 120 degrees difference. Instead of doing them all as separate ones like this, whoops, I didn't need that to go away. Now it's back. Good, we can see it. So I could say pi over 2 plus 2 pi n and plus 2 pi n and plus 2 pi n, but I can also say that we're at pi over 2 plus, for 120 degrees, is 2 pi over 3. That's as if it was 120 here. So I could say 2 pi over 3n. And that would be going one pi over 2 times one of these would get me here, times 2, times 3, times 4, times 5, times 6, times 7, times 8, times 9, times 10, times 11, times 12, 13, all the times around, or going backward. So this would be all solution. This is a cool problem because all 3 answers are all interconnected the same distance away from each other. Oh, that is much nicer than writing pi over 2 plus 2 pi n, 7 pi over 6 plus 2 pi n, and 11 pi over 6 plus 2 pi n. So this is still correct, but it's not really the nicest way or best way. It's certainly not the most efficient way to do it. So now you have seen how to solve a number of the equations for restricted domains, such as within the unit circle or part of the unit circle, and for all solutions, all possible solutions. And you've seen a number of techniques. In this one, you went and used one of the identities, a Pythagorean identity, in order to get us to the point where we could then do a factoring, a trinomial factoring, in order to separate them with the zero product property. And other ones, it's different techniques. This one, square rooting both sides, this was just algebraic techniques that we used. But those are pretty important, I would say. Here, this one was just normal trinomial factoring, but pretty important because it helped get the answer for it. And back onto this one where it was taking out a common factor and then using the zero product property. And then back on the first one, it was just a simple algebraic technique. So all of these are good examples of things to do for each of these types of problems. I hope it helps with understanding and learning this section. Thank you for watching and listening.